Okay, hello, this is my Caesar Cipher programming task. My name is Taj, and I'll just run you through the code really quickly. So, line 1, we initialize the dictionary named letter frequency. This data helps structure each lowercase English letter to a decimal value, representing its frequency in standard English text. These frequencies are crucial for later for the statistical analysis during decryption. Here, each value is defined explicitly for all 26 letters A through Z. For instance, A maps 8.17, meaning that under the lowercase a appears roughly 8.17% of the time in typical English text. The subsequent line continue this pattern, ensuring the frequency profile is available for our analysis function. This closing line completes the definition of letter frequency dictionary, making it a global constant accessible by frequent functions. Then on line 10, uh, we begin defining the function score text by letter frequency. The function is to compute a numerical score for a given text based on the sum of the individual letter frequencies, which is used later to access the likelihood that the text is valid English. Within this function, we have the first operation that converts the entire input string into a lowercase standard library method. This ensures uniformity because our dictionary keys are in lowercase, thus preventing case mismatches during lookups. This uses the .lower function. And on line 13, we initialize a variable called score to 0. This accumulator will store local frequency score as we process each character in the input text. Then we enter a loop that iterates over each character in the normalized text. This is a linear transversal, ensuring that each character is evaluated individually. Inside the loop, a conditional check determines if the current character is alphabetic. An example would be A being a letter, but it wouldn't detect numbers, so it would return score. And then for line 18, we would for each character that passes the alphabetic check, the dictionary letter frequency before, which we mentioned up here, we then query it using the .get method. This method returns a corresponding frequency value if the character exists as a key. Otherwise, it turns 0 by default, then the value is retrieved and added to the score accumulator. Then, after processing all the scores, the function returns the computed score. This score is quantitatively represents how well the letter distribution of the input text conforms to standard English. Next, we define Caesar's Cipher encrypt function. This function implements the Caesar Cipher encryption algorithm, with shifts each alphabetic character by a specific key amount. We initialize an empty string called encrypted. This variable will be used to accumulate the encrypted output character by character. We loop to iterate over each character in the input text. This loop ensures that every character, whether subject to encryption or not, is processed. For each character, we check if it's alphabetic using the isAlpha method, as mentioned before. This condition prevents non-alphabetic characters from being processed by the shifting algorithm. For alphabetic characters, which we checked for before, we determine the acyli base value using the shifting process. If the character is uppercase, we set the base to the acyli code of A. If it is lowercase, then we shift the acyclic value code to A underscore. That's the key difference. Uppercase, we change it to acyclic A uppercase, and if it's lowercase, then we shift it to A. This ensures that the encryption preserves the case and correctly wraps around within the alphabetic range. The core encryption operation is performed here. The acyclic code is adjusted by the subtracting base, adding the key, and then taking the result modulo 26. The modulus operation ensures that the shift wraps around from Z back to A. The resulting value is then converted back into a character and conjugated back into the encrypted string. For characters that are non-alphabetic, the program enters the else block. Within the else block, the character is appended to the encrypted string without modification. This ensures that punctuation and numbers and spaces remain intact within the encrypted message. After the loop completes, the function returns the full encrypted string. This is the final output of the encryption process. Next, we define the Cipher decrypt function, which is responsible for reversing the encryption process. Rather than implementing a separate decryption algorithm, we leverage the encryption function itself. Inside the function, we call Cipher encrypt, but with the same text, but pass a negative value of the key. By inverting the key, the encryption function effectively shifts characters backwards, restoring the original text. Next, we define crack Cipher fast. This function is designed to break the cipher without prior knowledge of the key by evaluating all possible shifts and scoring the results. Within this function, we initialize an empty list named potential results. This list will be used to store tuples containing a shift key, the decrypted text for that key, and its corresponding frequency score. Then we iterate over a shift value of 1 to 25. The value 0 is omitted since it would yield without the original text, making the non-information for the cracking process. For each possible key, we call Cipher decrypt to obtain a possible candidate plain text. This operation applies the inverse shift to produce a potential decryption. Then we calculate letter frequency for the candidate by invoking score text by letter frequency. Then this scores as the heuristic for determining how likely the candidate is valid English. The current shift key, the candidate decrypted text, and its decrypted score are bundled together in a tuple, which is then appended to potential results for later evaluation. After testing all possible shifts, we sort the potential results list in descending order based on letter frequency. Sorting by score priorities, candidates that statistically match letter distributions more closely. A header is printed to indicate that the following outputs will most likely show the most likely decryption results ranked by their computed scores. Then we loop through to the top 5 entries, just the top 5, so you can comprehend what it's saying. Then we uses its letter frequency to 4 digits, which is the .44. Then this shows a detailed output, which provides a clear insight into which decryption option is most statistically valid. The main function is defined next, which provides sorry, I took a water there. Which provides command line user interface to interact with the tool for decryption or ciphertext cracking. Then the program prints Cipher tool to the console. This output serves as a visual header informing the user of the application's purpose. Technically, this is a standard output operation which writes a string to a stdout. The string prints encrypted message. This line provides the user with a clear selectable option. It leverages the standard print function to output a string that denotes an actionable command. The next 4 lines from 59 to 62 do almost the exact same thing, just with different purposes. Like 60 is for decrypting and you'd enter D. 61 is for cracking and you'd enter C. 62 is for exiting and you'd just enter X. Then it asks choice, which it prompts the user to choose an option. The input is received by the input function, which reads a line from the standard input. The dot strip method is applied to remove any heading or trailing white space, and dot lower converts the input into lowercase, ensuring the uniformity regardless of how the user types their choice. So that this dot strip function I added, so if you did accidentally a space and then you click D, it would still go to the decrypt function. Or if you did a D, then a space, and then click enter, then that would still go to the decrypt function. Then a conditional statement is normalized user input equals E. This comparison is crucial for branching the program's logic to the encryption functionality. It uses simple equality operator for string matching. If the encryption is selected, the program issues another prompt asking for the plain text message. This input captures the raw string that the user wants to encrypt. The message is stored within a variable for subsequent processing. The script enters a loop designed to validate the shift key input, and the main purpose of the loop is just to check if the valid integer range is in 1 to 25. It means it's just a defensive measure in case somebody accidentally clicks a non-numerical value for when they're choosing, I don't know how you say this, when they're choosing, when they're either encrypting or decrypting a message. Within the try block, the program prompts the shift key with enter a shift key from 1 to 25. This input is converted into an integer using the int function, ensuring the variable key is of the correct data type for algorithmic operations. Then we can use a conditional statement here, which verifies the key is within an acceptable range from 1 to 25. This is essential because without it, you could enter anything and that would run, and then that would break the program because the pass code does not work and it's just redundant. And then if the key meets the criteria, then the loop terminates using the break statement. This locks the valid key and moves the program forward. If the key is not met within the valid range, the program prints saying that it must be between 1 and 25. This informs the user that constraint and prompts them to try again. Once a valid key has been confirmed, the encryption process invoked with the provided plain text and key. This performs the character shifting algorithm, returning the encrypted string, which is then stored for output. The encrypted message is then printed to the console. The output is formatted to clearly label the result as encrypted message, thus giving immediate, unambiguous feedback to the user. Input is made to pause execution so that the user can it's intentional and allowing the user to read and comprehend the output before the screen is cleared. The clear function just clears the screen so that the user can get a clear GUI that they can read on after. Now the program evaluates whether the user's choice was whether they entered D for encryption. This branching statement adds another conditional check that directs the flow of the encryption logic. If the decryption is selected, the user is prompted to input the ciphertext encrypt message that they want to decrypt, sorry. The user then similarly sorted to the plaintext, ready for processing by the decryption function. While another loop is initiated to validate the shift key for decryption, the loop ensures that the provided key is a valid integer and within that range, mirroring the logic used for encryption. The try block again is used to convert the decryption key from a string to an integer. This safeguards the program against invalid and potential runtime errors. The user is prompted for the shift key, and the input is converted to an integer. The conversion is crucial for algorithmic decryption process that follows. A conditional statement checks if the key falls within a valid range 1 to 25 again, maintaining that it's necessary for proper encryption. Upon validation, um, upon valid, upon proper validation, the loop is exited using break, ensuring that the correct value is used in subsequent operations. If the key is not entered within the valid range, then an error message is printed to indicate the requirement. And in the event of a value error during conversion, the error is caught and the corrected message is printed, reinforcing the necessity of a valid integer input. The error handling mechanism is robust for robust GUI. With the validated key, um, the decryption function is called using the provided ciphertext key. Intentionally, this function applies the inverse of the encryption algorithm, restoring the original text. The decrypted message is printed with a descriptive label decrypted message, providing the user with clear feedback on operation success. Another function, input, pauses the execution, allowing the user to review the decryption output before the screen is refreshed. This pause is intentional and I added it so that the user can read what it's saying. Then the clear function clears the screen so the user does not have all the clutter. Then line 100. The script checked if the user's choice is C, which corresponds to the automated cracking functionality. The conditional directs the flow towards the cipher cracking routine. If the cracking option is wish is selected, the user is prompted to enter ciphertext that they wish to analyze. The input is stored for use in the automated process. The crack sees a cipher function fast, refers to the defined function that we went through earlier, and the fast version because it uses letter frequency rather than a dictionary. This function systematically tests all possible shift keys, applies frequency analysis to each candidate, then outputs the top 5 statistically likely plaintext. It intentionally uses iterative loops, tuple storage, and sorting algorithms based on computed frequency scores. Pause again is introduced via input. This allows them to examine the cracking screen before the screen is cleared. The clear function is called to reset the terminal, maintaining consistent and clear user interface for the next operation. Next, if the the program checks if the user's choice is X, which signifies a request to exit the tool. This conditional branch ensures that the application can be terminated gracefully. If the exit is selected, a farewell message, "Thank you for using Caesar Cipher tool, goodbye," is printed to standard output. This provides closure to the user interaction and confirms that the program is about to end. Then the break statement is executed, terminating the infinite loop and effectively ending the interactive session. This is a key control mechanism because it ensures the program does not run indefinitely. Next, in the else branch, which catches any user input that does not match the valid options from E, D, C, and X, an error message is printed. This informs the user that the input was invalid and prompts them to try again. While outside the loop, the script contains a conditional check, which tests if the module is being executed as a main program. This is typically done using the name variable to distinguish a direct execution and importation as a module. This is a technical check. It's just common work, and it is to standard practice in Python to prevent unintended code execution. Then, if the statement is true, which it is, the script is executed directly. The main function is called, which starts the interactive command line interface. This is the final invocation that ensures the program is being, which ensures that the program logic is begins only when the script is run as the main entry point, making it modular and reusable, so you can run everything else and you don't need all the extra stuff. Alright, so now in part 2, I'll show you how my demonstration of my Caesar Cipher task works and everything about it. So I'll walk you through each functionality of my program, from encrypting to decrypting and automatically cracking ciphers. Let's get started. I begin by running the program. This tool displays Caesar Cipher tool and presents several options: encrypt, decrypt, and crack, and exit. I'm going to select the encryption option by entering E, and the program prompts me to enter a plain text message. And now, as shown before in my previous part, I can actually enter a space, maybe before or after. As you can see, there's a space here, and I click enter. And for this demonstration, I am going to use specifically cautious sentence that contains some obscure words and intentional misspellings that you can't get from a dictionary. So I'll do xylophotic, dyslexic, Phalangomoria misspells, unorthodox, lesgions, discombobulating zygomary. Now if I click enter, next I'm prompted to enter a shift key between 1 and 25. I choose the shift key 7, and then the tool processes the text, shifting each character by 7 positions in the alphabet. The program outputs the encrypted text, although the text now appears as an unintelligible string of characters. The underlying encryption process has correctly transformed our input. Now, if I just copy this like this, copy that, and I just paste it up there, and I fix this up. Yeah, that's good. And then I'll just keep that up there. I'll copy that. And then I can go enter to get to the next part. And then next I will show you the decryption method, which I can enter by clicking D. Now the program asks me for the ciphertext I want to decrypt, and I will copy and paste the ciphertext produced in the encryption step. So I copy, and then the program prompts for a shift key, and I'll enter the same shift key as I used before, which is 7, and this decrypts it perfectly, the same thing as it was before, and the tool processes the input, reverses the character shift, and outputs the original sentence as it was entered. xylophonically dyspeptic, phalangoria, misspells unorthodox like Ledaxians, discombinating zoomorphy. This confirms that both the decryption and encryption functionalities are working perfectly. Now I'll demonstrate the cracking feature. I select the cracking feature by entering C. The program asks me to enter ciphertext that needs to be cracked. I'll provide the same ciphertext that I received from the encryption step that the program does not know of. And under the hood, the program tests all possible shift keys, applies each key to the ciphertext, and calculates a score, each resulting text based on English letter frequencies. Although our sentence contained uncommon words and an intentional misspelling, the overall distribution of letters allows the program to determine which decryption most likely resembles standard English. Then the tool displays the top 5 decryption candidates, with the candidate that has the highest frequency score appearing first. You'll see that the correct decryption, our original sentence, has come up as the first candidate with 459 score, with others scoring 400 and a little while off 450. This also demonstrates the effectiveness of our frequency analysis even on challenging text, meaning you don't need a dictionary, you don't need to shift through all 10 million possible combinations of words and everything like that. So that's why I've chosen to do the letter frequency path. And finally, I can exit the tool by simply pressing X. The program terminates with a farewell message that concludes the demonstration of our Cipher tool. In summary, I successfully showcased encryption, decryption, and cracking. Thank you for watching this demonstration. I hope you run. Actually, no, I'll show you before I go. I'll show you that it can handle messages well. So I click ABC 1, 2, 3, and if I shift key, say I click an incorrect numerical value, say if I say 99, then it says the key must be between 1 and 25. And say if I do A, then it asks me for a valid integer, for 5, and then it shows the encrypted message. Same for decrypted message, ABC 1, 2, 3. If ABC 1, and then same thing if I click 0, same thing between 1 and 25. 3, and then if I want to crack, same thing. Well, I can't really break this one, but I can do symbols like that, and then it scores, letter frequency, same thing as before. Anyway, thank you for watching this demonstration. I hope this run through illustrates the full power and versatility of my Cipher tool. Goodbye. Thank you for watching.